Hello guys, first of all I want to welcome you all to my YouTube channel Cocktail 2. Today we are going to see how to do computational fluid analysis over 3-dimensional elliptical nozzle. Before going to our session, I want to give a short intro about myself. I'm Vignesh. Basically I'm an aeronautical engineer and working in product development domain. I have 3 years experience in CFD, FEA, product design and development. This is my first video in educational background, so I need your support. Well, English is not my bilingual language, so please take my apology for any mistake I have made in this video. Let's go for our section. Now I'm going to show you the CAD model of our analysis. This is our CAD model which is created in SolidWorks based on our requirement. See, this design was developed using method of characteristic for CD nozzle. This is our CAD model. Now we have to go for an analysis section. Now I have to open Workbench. It's taking time because I have lots of stuff in my laptop. It's taking too time. Sorry for inconvenience. Oh, it's taking too time, man. Yeah, it's now ready. We are going to choose a Fluent Solver. From that we are going to do our analysis. Just click the Fluid Flow and Fluent Solver. It's opening right away. Now I'm going to open Design Model A in order to import our external geometry of CAD model. It's opening right now. See here, starting Design Model A. It's taking a little bit time. Yeah, here we go. First of all, I'm going to import external geometry of our CAD file. Before that I want to copy the where is my file are located. Just I copy the folder file location and going to import the geometry. This is a CAD model of elliptical nozzle, edited one. Yeah, just open it. And now our model are imported and we need to give a generated, so that only the model are going to generate. See, this is our CAD model. Is a convergent section or the divergent section. So there is no any connection or any assemble model in this one. This is a single part. See, this is just a single part, so we don't need to check a shared topology, but I'm going to show you. I can give a shared topology. The purpose of the shared topology is to check the geometrical error. If it is if you have some external parts of 2-3 more parts, if while in connection means we need to check that one. Now I'm going to generate the shared topology. Yeah, it's ready. If it is green tick, is okay, geometry is fine. If another like green like yellow tick and red tick means it's some problem is there in geometry. So in our model everything is fine. Okay, now it's fine for this section. Now I'm going for our mesh. Now I want to close this Design Model A. It's already updated in geometry here in Workbench. Now I want to open the mesh section. Yeah, it's opening. See here, starting meshing. So it's take a little bit time to open. Yeah, it's going to open. Okay, this is fine. Our model are imported here. So I'm going to choose. What is this? I just want to close this one. Yeah, I'm going to choose a mesh method now. Just right click the mesh icon and insert, then click a method. This is a blend shape structure, so I want to choose appropriate method like select method. Before that I need to click a geometry file. You need to give body element icon here, and in geometry click it and apply. So the whole body are selected now. So now we are going to choose the method. I'm taking sweep method for our convenient. So the free face mesh type is taken as in quad try. There are several options there, like all try. Only the if you took try, all try means the only triangular mesh only taken. Now I'm took both the quad and try, so it's not a problem. And also the type, there's a two different types there, on the element of sizing and the number of division. Now I'm choosing number of division, and the soap now division are taken as 50 for our convenient. You may give on under itself, it's not a problem here. So I'm going to give 100. Just enter it. Okay, the measure is okay. Now I'm going to the edge method. So in order to get the edge method, click the edge icon and select the edges of our geometry model, both the sides, edge, backside edge as well as the outer edge. I'm selecting each and every edges of our CAD model. Yeah, if I'm fully selected all the edges, it will be covered. Now I'm going to insert sizing. Yeah, see, it says edge sizing. So the total number of edges are selected as 10. It's already noted in the details in the taskbar. Now the type is selected as the element size. Now changing the element size into number of division. For our convenient, I'm going to enter as the 100 division as per the sweep method already we have done. Now click enter. Then you have to go to the further quality checks. For that I am consider the sizing. See here we have now advanced size function. In that I am going to choose proximity and curvature. Then for our quality purpose I am choosing the medium size mesh method. I am going to choose the transaction as fast, and everything is fine. Yeah, we don't touch any other things. It's all default is enough sufficient for the inflection option, smooth transition we have to. So there is no problem there. Just generate mesh. Yeah, the process are going well. It's taking time. Maybe we can check the mesh quality after generating the mesh. If we need to give a fine mesh, it's also sufficient. See the edges also we can get a fine meshes in that. So it's look good. It's fine for our simulation. So it's not a problem. For our convenient, I want to took a section plane to check the inside crosscut view of our section. So just click the section plane, the cut plane. make the bot visible. See, now checking the mesh. Yeah, it's look fine, right? If you want more fine meshing, it's not a big problem. You can do it for yourself from here. Relevant center take medium to fine. If take fine with the nodal element and nodal element taking, you will see here our strategy shows the node is 1,36,000 and the element is 1,36,000. If we need fine measurement, you can do. So for your convenience, for your learning ability, I want to resize this one. So now I'm going to do the relevant center medium to fine. Yeah, let's do yellow color. So we need to generate mesh over that one. So here it's processing. It's take a little bit too time because we're giving the fine mesh. So it's not a big deal to do. Well, it's still upgrading. It's taking a little time. Yeah, we got the one. Yeah, here the nodes are increased from before. Okay, now I'm going to close this mesh. Before that, I want to show you how to export the mesh report in that. See here. Here the export is there. From that way we can export our mesh report as well. I'm just copy the required folder on that. So just save the report there. We can took our mesh report afterward. Before that, I just named the section for our simulation requirement. So this is the inlet section and this is the outlet section. Yeah, so for that I want to name the section. Just click the face, click it and right click, then create named section. The name is inlet and click OK. Similarly, and again to the external section and create named section as outlet and hit OK. And other than inlet and outlet, the other section are 1. So like this, create intersection and put the name as what. Hit OK. So now you may see this is the inlet one. This is the outlet one, and other than that everything is what. So now everything is fine. The mesh is also good. It's looking good. So I just want to close the meshing part. Yeah, and I'm going to it's may update from here. Just right click and update. It's updating. Now just here open up the setup. I'm giving the option as a double precision, and the processing option is going to give us the parallel, and I'm choosing to process from our local machine. Then hit OK. Now the solver are opening. Let's see from here starting Fluent. Taking a little bit time to process overall the model, so we have to wait until that. It's contribute all the works what you have done previously. Yeah, now it's look fine. Just maximize. I already told about the mesh things. Yeah, we are going for our setup process. Now checking out the scale, so it's all the cases are in meter only, so it's not a big deal. So proceed. You may check from the mesh process and the face area, assembly max area, those things. The report quality shows there how the mesh quality is. From this you can see the orthogonal, minimal orthogonal quality as well as maximum orthogonal quality as well as the aspect ratio of a mesh. Now we are going to do a solver as a density based solver, because we are going to use an high speed. So this is the high speed compressible flow, so we are going to choose as a density based solver, and as well as taken as a steady state, so it's not a big deal. Now I'm going for the model in which the energy I'm going to on the energy equation, and the viscous are going to take as the viscous model taken as a K epsilon model, and the standard the all function are enabled to 1 and the other things are the default one, so hit OK. So that's it for the model. There is no essential acoustic or discrete phase species heat exchanger, there is no need because we are not going to concentrate on that. Now we have to choose the material. It's already took one. Everything was taken as the fluid is taken as an air. Now I'm going for the silicon condition. So only one part we have, so that part we have taken as a fluid medium is fluid, so it's not a big deal. Now we are going for an boundary condition. Well, in inlet we are going to taken as the going to choose the inlet as pressure inlet. Yeah, I am going to gauge total pressure as 3 bar, so 3 e power 5 and hit OK. Okay, let me check again. 3 bar, and the outlet is taken as the pressure outlet. It's not a problem. So the wall, so we did it, we taken as the no slip wall, and the wall motion is taken as the stationary wall, so it's not a problem. And the dynamic motion, no need of that one. The reference value are taken from the inlet, and the reference one from FOD4. That mean that's our CAD model. All other things are taken as the default. Here see the density is 1.225, that's our constant air density, and the enthalpy and the velocity are taken as a based on our input given. Here once again I wanted to check the inlet pressure what we have to give in the it's 3 bar, it's not a problem. So okay, it's fine. Now the reference value, everything is fine. Now in solution model A, I'm taking the flow is a second order upwind, as well as the turbulent kinetic energy is taken as the first order upwind. You may choose the second order upwind for complicated model. For now this is enough, highly sufficient for us, so isn't a problem. So in solution control, the turbulent kinetic energy is taken as the default one. These things are underrelation factor. It's very important one to for our in some model reverse flow occur. Maybe in our model also may reverse flow may be occur, because we are not taking fine good quality mesh. I think it's sufficient. I'm just showing the tutorial. We can do like this, so I'm taking this in default one, so we don't have to change these things. Now I'm going for a monitor control. The residue, just hit the liquid, and in absolute criteria I'm going to add 10 power e4 for continuity and x velocity, y velocity and z velocity. The main purpose of the thing is to delay the convergence solution, because how much we delay the solution means we get more appropriate result. So I'm taking the e power 4, taking e power minus 4, so everything is okay here, so just hit OK. we don't need to drag left, but if you want to drag values, just create the plot here, drag and like cd print to console and plot and wall. Just I'm going to give you the example, see print to console plot and choose the wall. I'm checking the cd is plotted, as well as create the lift also class from print to console plot wall. Also now choose as wall and hit OK. So here we have a cd as well as here, and as well as my residual or residuals. So the solution, just initialize the solution. Initialization process are going here. Yeah, now the initialization was completed. And there is no need to do autosave here because I'm using UPS, so no problem in any power option, so it's not sufficient here. So in run calculation I am going to give the iteration as 2000. Okay, just give 2000 and calculate and give the calculated. It's the solving progress are going to start. Yeah, it started. With this VDCL plot, we can go for our residuals. Yeah, here the residual costs are going. So I have already given us 2000 iteration, so we have to wait until that. So what I'm going to do is I just want to stop the video because it takes too time for 2000 iteration. After that, until that I want to pause the pause the recording. After getting 2000 iteration or the conversion happen at this time, I'm going to restart my video. So until that I just want to pause the recording, so we have to wait patient until that. Yeah. Hey guys, I have stopped the simulation after the 200th iteration. Check this is the convergence plot. So as per our previous inputs, I have stopped the iteration at 2000 residual. So this is the residual part of our simulation. Now I'm going for the result section, opening CFD post, that means the results. Yeah, it's opening now. CFD post are opening. Post processing is one of the art. Yeah, it's a very important part in CFD analysis because the overall progress are going to explain in post process section only. Now I'm going to do step-by-step process for your company. Now I'm choosing the location and taken as the plot. Yeah, the plot name are given as velocity contour in XY plane. Yeah, hit OK and choose manage the finish all the move and type is not a big deal. Constant. Yeah, and hit apply. See, now the plane are created in XY plane. Yeah, just unhide that one and click the sorry, I have named this wrongly. Just change this or duplicate it and line XY, hit enter and delete this velocity Yeah, now we have created an XY plane. See here, it's one. Similarly, create another plane as X Z, hit OK and apply it. In XZ plane we have to choose the plane as XZ and hit enter. Okay, see here we can already choose the XY plane and XZ plane. Now we hit OK and unclick it. Now I'm going to contour. Just click the contour and name as the velocity contour. Contour X Y. Hit OK and we have taken a variable as an velocity, and the range is taken as you can take global, local as well as the user specified. I'm going to take the global one because based on our simulation performance it will going to display, so isn't fine. The location are taken as XY plane. Just apply it. Yeah, this is our velocity contour for our model A. For default legend view, take the values, and also for fine visibility I just want to choose an view from n-z. Yeah, it's okay. And the foreground I'm going to increase the contour one as 100. Yeah, it's look fine now. Check the velocity is maximum at the throat. Obviously we know that one. See, the maximum velocity is 8.49 10 to the power of 2 meter per second. Yeah, this is the velocity contour for XY plane. Similarly we can do it for XZ plane. So for that I'm going to duplicate that one and put the name as XZ. Hit OK. It's created here. And that one I'm going to choose the location as XZ. Yeah, and apply it. Yeah, see, you may see here we already have an XY plane and XZ plane. Similarly we're going to take pressure contour or temperature contour, vice versa, whatever the need we can took from here only. I'm simply gonna duplicate that one and change the name as pressure contour in XY plane and hit OK and hide the velocity contours in the pressure contours. I just to change the variable as pressure and apply it. Yeah, now this is the pressure contour for XY plane. Likewise you have to take a pressure contour for XZ. Simply duplicate this one and change the name as pressure contour in XZ and hit OK, and in that one just to change the variable as variable from velocity to pressure. Yeah, see, now both got velocity and pressure contour from each and every second. See, this is the velocity for XY plane, the velocity contour for XZ plane. Similarly, pressure contour for XY plane, pressure contour for XZ plane. So okay, it's fine now. Vice versa, we can choose again, duplicate that one. We can take in any temperature contour. Likewise, just change the variable for whatever the things you need. See, the temperature and the turbulent kinetic energy and other stuff is there, so you can choose from that one. I just simply sufficient. This is sufficient for velocity control. Now I'm going to show you how to take an velocity vector. Yeah, just click the vector one and change the name as vector xy in xy plane. Just hit OK. Yeah, from the location I chosen as xy plane and just apply it. I forgot to do, yeah, xy plane, just apply it. Yeah, for our clear view I just want to change the preferred camera. Yeah, just unclick the wall as well as wireframe. From that one, just change the turn factor as 2 or 0.5 now. Yeah, one is sufficient, default one. And the color, you may change the line arrow and change the symbol size as 2. Yeah, it's enlarging. You may view from here. Yeah, this is the flow path from X1 for clear view. And just click the yeah, this is the things from inlet to outlet. The velocity is maximum at the through section. This is how to do for velocity vector for each and every plane. So this is sufficient. Similarly, I am going to show how to take a streamline path. The streamline name, change the name as XY. Hit OK. There's the two options: the 3D streamline as well as surface streamline. Just initially I'm showing the surface streamline. The techno just an plain XY one. Just hit apply and hide the XY contour. See, this is the streamline path for our section. Just to change the points 20 to 250. Just hit apply. Yeah, this is the perfect view for surface streamline in XY plot. See, this is the one. Yeah, if you want to take for another XY plane, just duplicate it. Vice versa, just change the name as XY plane. Just hit OK. Generating that change the surface into XY. Just apply it. Yeah, you may see the surface plane here. This is the procedure to take the surface streamline for that one. Yeah, similarly, in order, if you want to capture the flow from inlet to outlet main, just create another streamline. Just name the streamline. Just apply it. It's the error man. Yeah, location inlet. Yeah, apply it. Just unhide the XY streamline and XY streamline. See, just change the points as 250. Yeah, this is detailed things. This is a 3-dimensional streamline. So you may hide the lines from here. Before that, I want to show change direction both forward and back. Just apply it. Now, if you want to get a clear flow path, just see from the animation plot is the see here. Just put the animation plot and in streamline, slow down the frames. Just play it. See, this is the our flow process. Yeah, it's stuck slowly. Yeah, you see it now, right? If you want to slow down, just stop it. We don't want to see the lines. It's simple. Just go to the symbol and hide the lines and apply it. You see, you know at the lines. If you want to slow down the animation part, just here. See, I'm going to given us the minus 20 seconds. As far as the maximum time is 20 seconds and the max interval is 0.5. Just apply it. Yeah, see, now play it. Well, it's look fine, right? This is the things we have done. You can save these things, save the animation from here. Just stop that one and here. Just save movie from appropriate folder you want. From that you can save the file as some video I don't want to save this one now, so I just unclick on this, close the video. This is see, this is how to do. It's a flow path for our 3-dimensional elliptical CD nozzle. Yeah, and another important thing I'm going to show how to do take a maximum to the maximum values from each and every sector. See, there is here calculator, and that functional calculator is there. The function is there, location is there, this is there. Now I'm taking my one is the maximum value. That's me the max. Yeah, check the maximum value, and location is taken as an outlet. The variable is taken as the velocity. Just apply it. The maximum velocity at the outlet is 707 meter per second. Similarly, is in inlet, it's changing. Just calculate inlet 142. Obviously, the inlet velocity is around 142, and the outlet is around 770. So obviously, the velocity value is increased in this CD nozzle, elliptical CD nozzle. So it's look fine. And if you want an average velocity, you can choose from here. Just choose the average, and the inlet velocity, just calculate the average velocity of the inlet. Similarly, you can calculate the average velocity at the outlet. Yeah, and the another things, you may check various value like pressure, temperature, and those things as well. Just take average outlet pressure. At inlet, just apply it. Yeah, you may get around 3 Pascal. Yeah, this is the fine. These are the things I've done in post-processing. You can take an every each and contour as well as value. I already created the post-processing in PPT. Check this one. Well, this is the residue I have taken. From top to bottom, this is our geometry and meshing. It mesh edge sizing as well as subtool method. This is our boundary solver condition steady state density based KFCL model. And second order of being and first order of being pressure inlet, pressure outlet. Both are taking pressure inlet as inlet and pressure outlet. So this one is understanding. This is the boundary condition. The initial inlet pressure is taken as a 3 bar. And mostly for this constant density. See, this is residuals for our one, and I have to take on everything here. Velocity contours, XY plane, pressure contour, XY plane. Similarly, temperature contour, XY plane, temperature contour, XY plane, surface plane, velocity vector. Each and everything I have noted from here. See, this is the another one. I have took the plane in between the model. That's the YZ plane. Similarly, we have done before. Yeah, this is the video I have captured for everyone. Just to play it. Yeah, this is going good. These are the things we have done here. Just minimize it and save the file. Yeah, a file is saving. This is done. Our post processing and the complete simulation progress are finished now. So this is the things we have learned from today's session. So guys, I need your support. Based on your response only, I'm going to upload more video in CFD as well as FEA. So please subscribe my channel for future convenient. And if you like this video, just share this video to your friends and learn CFD from basics. If you have any queries, just comment in comment section. I will here to respond as soon as possible. So thank you guys. Don't forget to subscribe my channel. I need your support. This is my first educational background video, as I told earlier. So I need your 10% support. From that I can get motivate myself to give a more number of videos for your learning process. So guys, thank you so much for watching this video. So I'm going to sign off. Thank you guys. Just subscribe my channel.